course of talks. Next talk will be by Sergey Nazarenko from Warwick University, Wave, Turbulence, Solved and Open Problems.
Okay, so wave turbulence. So first of all, what we mean by that, basically quite broadly it can be defined as non-equilibrium statistical mechanics of weakly nonlinear dispersive waves, right? So non-equilibrium of although recently there's been quite a lot of effort done to include coherent, strongly nonlinear coherent structures into the description, and it's in most of the applications it's important. So perhaps worth a week, at least in in some approaches, some applications can be removed. But I will be talking about weakly nonlinear most of the time today. So examples, of course, just the waves you see on the sea surface after storm. That's most typical. So the waves due to gravity, due to surface tension, sound waves would also be of this kind. A lot of different waves in plasmas, waves in Bose-Einstein condensation play an important role. In non-equilibrium condensation or nonlinear optics. So this is, you might even consider it as one of the canonical sort of examples described by the nonlinear Schrödinger equation. So that would be Beck, which they call it Gross-Pitaevsky equation, so nonlinear optics. So believe it or not, also recently there was some work where they also derived a bit like that for the waves on elastic plates. So and they now doing experiments in École Normale in Paris is pretty much like that. The last time I saw it,
You can't see that.
that is transparency. So they had a paper, Sergio Rica, Christophe Jusserand, and Gustavo Durin. They had a paper called a PRL called "Can You Hear Kolmogorov Spectrum?" And so basically, according to them, that's what we hear, right? So they have, well, maybe bigger size. Sometimes it's plastic, sometimes it's metal shade with which they have a loudspeaker to excite waves, and then they have different ways to read the waves from it by laser, scatter laser.
So the nonlinearity comes from the deformation of the nonlinear.
That's right. So
of the plastic.
Sure, nonlinearity is more or less the deviation of the plate from its horizontal. So the nonlinearity parameter is the slope. So the slope is the slope is small, nonlinearity is small.
Sergey, the most marvelous nonlinear acoustic device is the symphonic orchestra tam-tam, the great gong which goes brrr. It has this wonderful rising frequency. Now,
that is a good point, because I guess one additional thing you need to ensure that the dissipation is smaller than the nonlinear transfer. And you actually, if you're talking about transfer over over modes in wave number space, right? Yeah. Like what you're referring to, yeah. You need to make sure that nonlinearity comes first. So, and that's perhaps maybe worth studying it more closely. The properties of the spectrum and whether this.
Should be studied. Has it been studied?
I don't know. I mean, so I would guess not, but
So this one you were just describing with the so that has people have done numerics or done experiments with it.
they've done and they're still doing it. They continue in École Normale in Paris.
And did they see?
Nicolas Morand, I think.
And do they see the kind of?
They see spectra. They see some Paolo solution. They see slopes. I think there's a little bit of controversy that actually they don't see something that is predicted.
I see.
Right. So okay. So anyway, today I will be actually kind of in some way go in terms of approach very back to the origin of where first wave turbulence was proposed in the work of Pyrrhus in 29 in the following sense. Okay, so recently people kind of forgot this approach, but as a matter of fact, in his very first paper, Pyrrhus not only derived kinetic equation for the energy spectrum of waves, but also for the probability density function of the wave amplitudes. And and I think it's an important extension of work, because you might start asking questions whether assumptions about the Gaussianity and random phases used in wave turbulence approach are satisfied, because you're dealing with PDFs. You can start asking questions like that and study systematically fundamental assumptions. And also, if you have a question for PDF, you can ask whether you have situations sometimes when statistic deviates from Gaussian, and in what way can you observe intermittency in wave turbulence. Okay, and so these kind of things I will be talking about. So. Let's first of all, let me formulate the statistical setup. In terms of what kind of quantities we will be looking at. So they will be in Fourier space. So periodic box of dimension d. And so kind of with size of the wall L, so volume L to D, and Fourier transform with the following normalization. I'll choose. So or box. And I want to decompose so these are generally complex Fourier coefficients, which I want to use the angle and amplitude decomposition of them. So this will be intensities. Just positive reals, so intensity of wave. And phi will be the phase factor, so it will be just on the unit circle in Fourier space. So phi is something like that. And so you can right. So then also, because I'm in periodic box, the size of which I'll would like to take to infinity later on. So I will have Fourier space discrete. Let's say k, kx, ky for 2D, just illustration. Right, and let me suppose that there will be some maximum wave number, k max. So, which is, for example, due to dissipation at high wave numbers, or it could be, again, something artificial that I want to take to infinity as a limit later on. So, but I want to deal with sort of the discrete and finite set of modes for simplicity.
But we go to a lattice. You don't like the lattice particularly, like spatial lattice. Dennis dual is nice. And
yeah, so I would prefer to, sort of in linear approximation, the Fourier modes will be independent solutions. So, because in lattice they would kind of mix a little bit, and so. But in effect, existence of k max, in some sense, it's like having a discrete real space with minimal distance. So this is well, okay. So this is kind of, I can call it box. So let's say the total number of modes is n, and it will be on lattice in Fourier space. So now, so the total number of modes, so k max or k mean to power d, and k mean is 2 pi over L, size of the side of the box. So now I will just introduce shortcut notation. So let's say all sets of amplitudes and sets of angles for L, from this finite Fourier box. So I'll just, for short, so that I don't write it all the time, just write it like that. And so now I can define the PDF. So n, so definition, n mode joint PDF so which is function of all of the angle variables and space variables. As usual, it's defined in such a way that P n is theta, so product D so that this this kind of product is probability of every corresponding amplitude JL to be in the interval from SL plus DSL, and the angle variable to be in the sector of a circle like this. So zeta L D zeta L. Okay, so this way. Okay, so now So this is endpoint joint PDF. We can reduce the number of variables in PDFs as much as we want by integrating out, separately angles or amplitudes. In particular, the important one, so N mode amplitude only PDF. So basically, we just it will be only dependent on the set of amplitude variables, and we just need to integrate out all the angle variables. Okay, so we can also define one mode amplitude PDF. Integrating all the variables but one, all the amplitude variables but one. So let's call it P1A, or I just use it like that if for shortness. So now I want to define what do I mean by random phases. So this is definition, right? So it's not an assumption, I just define what it means, random phases. So basically, I just say that that all variables are independent of each other, or of anything, of amplitude. So independent random variables, which are uniformly distributed on the unit circle. So phases are not only random from 0 to 2 pi, but also, at each modes they're independent one of another. And so now there's a remark here, right? That actually a random phase is only not sufficient for well, actually, so remark so that this property is actually sufficient for kind of lowest level closure in wave turbulence, namely for derivation of equation for n-particle amplitude only PDF for closure for PAN. But insufficient for closures for one-point objects. And in particular, and respectively for spectrum as well. So, and of course, the spectrum, which is the moment of that. Okay, so well,
you can close the amplitudes, but you can't close the one-point amplitudes.
That's right. So I define amplitudes as for the square of the well, intensity J is square of width. So essentially, the spectrum will be L over 2 pi here times D, if we get dimensions right. So J, K, so this is the spectrum. And for this quantity, I can't get closed equation unless I assume something else for the amplitudes as well. So and this is kind of, sometimes slips out, this kind of fact from physics literature. Well, we hear RPA, random phase approximation, right? But in fact, what is actually done is done something more than just random phase. It is assumed that the amplitudes are also random. So, and I will therefore redefine what RPA should stand for. So, random phase and amplitude. And this now be RPA field. And so this is also definition. And by this definition, so first as in random phase, I assume all the phases are independent, but now actually not only phases, but also all of the amplitudes are independent random variables. So independent of each other, among themselves and of each other. And second, that phases, as before, are uniformly distributed on the unit circle. So, and as a kind of a remark, I can put number 3 here. So, form of the amplitude distribution is not specified. So, which means that this is slightly this is not necessarily Gaussian, not necessarily the same as Gaussian. So
So when you say all the phi's and j's are independent, are you also assuming they're independent of each other?
That's right.
Are you going to assume a particular spectrum for the J sub L's?
At the moment, not. So this is that's right. So this is at each particular
But they'll have a Gaussian distribution about 0.
Uh,
J sub L's.
Okay, look, for Gaussian distribution, the amplitudes, right, the PDF of amplitudes, okay, so would have to be exponential function. So this is called Rayleigh distribution. So because random phases, we actually did not specify this part. It's arbitrary, and this is actually this means we can be non-Gaussian, and this is kind of good news because, remark. So RPA is enough for WT, wave turbulence closure, of everything, of one-point objects as well, inclusive.
But now once you know the 1 point, you know everything, right?
Exactly. No. I mean, no. 1 point is a projection, right? So
They're all independent. Oh, that's what I'm confused about.
If they remain like that, then yes. But see, that's the thing, So what I'm saying that here I didn't assume anything about amplitudes, right? And I actually can derive equation for the joint PDF for amplitudes, and it's not necessarily with random amplitudes. And I can substitute the initial PDF such a product factorized in amplitudes, such as has independent amplitudes.
This has to do with your random phase and amplitude have to do with your initial data, or?
That's right. So at the moment it's just definition.
Well,
Right.
basically,
About and in wave turbulence it will be, I will assume it for initial data,
okay.
and then I will check if its statistic remains, then I derive evolution equation at t equal to 0, right? So
And see how that
evolve it
evolves.
for nonlinear time, and see if it remains of the form that I assume. So see if I actually can
Preserve that structure.
Yeah,
Yeah, and you won't, right?
yeah.
Okay, I mean,
And
this,
well,
this, of course, this assumption is a little reminiscent of Boltzmann's Stossalon sites in the case of the classical kinetic equation. But of course, in that case, we know that in the low density limit that was considered by Bogusław and Grad, that in some sense that assumption becomes justified. Maybe not globally in time, although it's believed to be true there, but at least locally in time, we have a proof of it. I mean, is this supposed to be something that should come out of the weakly nonlinear limits?
well, that's what I exactly would, my kind of in the ideal world, that would be outcome if today somebody would actually be able to trigger some thought in this direction. Okay, I think there is a lot of similarity with with Boltzmann versus Liouville, in what I'm going to say, but maybe something can be said, right? So okay, so this is good because it now makes sense to derive evolution equation for PDF, not only so how it evolves study intermittency. So can now study PDF and not only spectra. And check the properties such as intermittent behavior and stuff. Okay, because if it was close to Gaussian, then I study spectrum and it defines the entire statistics, and all of that wouldn't make much sense.
So what are you going to see? Will this system, this wave turbulence, produce intermittency?
That's what I'm going to argue that it can. So well, okay, so. Another thing, in terms of definition. So a generating function and because I'm not going to actually for the space restriction, I'm not going to derive equation for n particle distribution function. I will mention the result. I will try to kind of go through most essential steps in one particle, one point derivation, and convince you that for multi-particle you just basically follow similar kind of route. And because of that, I'm not going to do multi-particle generating function. I'm going to do just one point generating function. So Z. And it's going to be amplitude only, so J function of lambda, J can be function of time as well. So essentially it's just the average, so it's mean value of of L over 2 pi to D lambda j well, okay, let's use L. Too many j's. So generating function is well, as usually it's convenient because you can recognize in it that it's actually well, if you actually substitute what it means, it's basically
Could you
just
write out that exponential, because there's a cord hanging over it from.
Like what?
I had the same problem.
We can't read the exponential because there's a cord hanging over it. So could you just rewrite it?
Yeah, I'll hold it for a second, so.
So the lambda is just the dual of the j.
Yeah, so J, okay, so, well, that's by definition of averaging. So let me call this thing as lambda tilde, so that I don't want to write all the time these things.
It's something over 2 pi to the d.
It's L over 2 pi to power d.
Okay, fine, thank you.
And so here S J D S J. So you can recognize as a Laplace's transform of the PDF, and that's so. If I derive equation for Z as usual, I can inverse for Laplace transform and get equation for a PDF. Same holds for if I did for multi-particle. So I just had multi-dimensional Laplace in amplitudes and Fourier in angle variables. Okay, and so in particular, well, I can say for the spectrum. So you can notice that for the spectrum, I just what I need to do, I just need to differentiate Z with respect to lambda and take it at lambda equal to 0, and that will give me the spectrum. Why? Because to differentiate with respect to lambda, you get a coefficient in front of exponent, which is precisely the spectrum, and then take it at 0. This means the exponent becomes 1, and so you get the spectrum. And you can have a higher momentum by more differentiation. So higher moments via more so differentiating that. So now, okay, now so these are the statistical objects, and
So you're not including or you've averaged out the phases in this picture. You're assuming that all the phases, always going to assume the phases are random.
only initial,
Only initially.
right?
Well then, how do I know that? Why don't I have to? Shouldn't I also include the phases in this?
Absolutely. So okay, so basically I could have done two things, right? So I could have considered the full endpoint PDF, assume initial random phase, and then turn the crank, and with all the phases and everything. But it's a long derivation. But in spirit, it's
Okay,
what I'm going to
similar.
show. So basically, what I'm going to show, I'm going to derive equation for one particle, one moment, one point, the objects, PDF, and the steps will be similar as for many more. But of course, by doing that, I don't justify it. I don't present justification or the original assumption. I only obtain evaluation equation at time equal to 0. But not, okay. So I only get z dot time derivative, right? So my goal is derive right hand side. Only at t equal to 0, and then I assume it holds the same equation holds for nonlinear time. Well, but to justify that, I would have to go and consider endpoint distribution function, which I won't do, but hopefully I'll show you the result, what kind of equation. Right. So let me now briefly tell you what am I going to do, kind of a plan. So how to go, okay, so first I start with equation with a wave equation, evolution wave. Okay, and do weak nonlinearity expansion. And at the second step, use RPA on initial data. Okay, so then I will discuss. I'll get evolution equations. For one-point distribution function, so therefore for the spectrum for any higher moments, and I will discuss solutions. What can I say new about solutions? So new solutions, non-Gaussian solutions, intermittency. And wave turbulence cycle. And well, hopefully I'll have some time, so I'll discuss the multi-endpoint statistics. And open problems. So for wave equation, well, okay, so it's always sort of a permanent quest for the simplest system to explain the whole thing of that. And well, I guess the one I found at the moment the simplest, it's Petriashvili equation. And this is actually for Rossby waves in some limit, with some thermal nonlinearities, whatever, So, and the equation is for the stream function, and so the equation is so x means differentiation with respect to x coordinates, so it's an isotropic. So d equal to 2 dimension.
So you have a Laplace, so it's cubic. You have a third.
So this is quadratic nonlinearity.
Yes.
So there will be a 3-wave process. So this is 2-dimensional Laplacian.
Yeah. Okay.
So this is time derivative.
But there are 3 derivatives. Did I understand that correctly? There are 3 derivatives on that side.
Yep.
Yeah.
True. So in Fourier space, So this is for people who, from Turbulence, probably familiar with the Rossby wave. So this is a kind of small deformation radius limit. And the nonlinearity not arising from U grad U, but from some other effects that are leading to so-called scalar nonlinearities discussed by Petriashvili.
So why do you call that Rossby wave when it has a nonlinear term, psi dx times psi?
Well, this is what Petriashvili calls scalar nonlinearity.
It's not what we normally call Rossby waves. They have a constant time deep psi dx. I guess. Oh, what do we could
So do you mean here or here?
Oh no, it'd be a completely different equation. It would be d dt of Laplacian psi.
Yeah, so this is already in the frame moving together with a Rossby wave. With,
the time derivative would act on a Laplacian. This is a different problem.
yeah, so this is already assuming that k rho much less than 1, and therefore you're almost non-dispersive. You go into a frame of reference and you do iteration, and you don't. So you replace time derivative with k beta kx. So you're almost moving with beta speed. Anyway, so let's not.
Oh, you move with the Rossby propagation speed.
Right. Yeah. Okay. So. So basically, my notations here will just for shorthand, etc. And this is the discrete delta function Kronecker symbol, k minus k1 minus k2. And so what I want to introduce here is a wave action variable. AK. So I'm normalizing my amplitude in such a way just to make the equation more symmetrical. And in fact, if this will be a true Hamiltonian wave action variable, but I don't want to discuss Hamiltonian structure right now. But so this makes equation look like this. So this is omega, by the way, so this is a frequency of linear waves. Omega k ak plus sine of kx Okay, so where interaction coefficient I introduced in case of this Petriashvili kind of nonlinearity is particularly simple. And then I introduce interaction representation variable, so bk equal to ak divided by some epsilon e to I omega kt. So interaction representation, and epsilon is just formal parameter to count the nonlinearity. It's much less than 1. So basically, this interaction representation variable is something that does not evolve in linear limit. So, and the equation becomes still still exact. Nothing was done in terms of expansions yet to it, but in very symmetric form. So we're introduced again for shorthand notation, omega of k minus omega of k1 minus omega of k2. So now let me choose time t, which is much greater than the linear period, characteristic linear evolution time, and tau nonlinear. And we will see for this particular system that it's actually going to be different by the factor of by the factor epsilon squared. So you could as well just say this is equal to 2 pi over epsilon omega to be right in the middle. And I know that actually here in the equation you see nonlinear time dynamical is 1 over epsilon, but due to statistical cancellations it will become 1 over epsilon squared due to random phases.
And you can control that, or that would be my sort of first mathematical question, whether you could actually control. This is exact equation, right?
Yeah.
There's no, you've made no approximations so far.
So far, no approximations. That's right. Okay. So that is the goal, to control. Okay. So I'd say the answer is yes in some parts, but you know, it's not. The story is not over. So that means that there's a lot of work to be done. Okay. So and we want to write our variable at time t, at this intermediate time between linear and nonlinear, as a formal expansion and nonlinearity parameter. And so in the zeroth order, of course, we'll get that B0 is just, it's not evolving, so it's equal to initial. So this is the linear approximation. And then in the next, what we do is we substitute this to the right-hand side. Because it's not evolving, we find for B1, we can integrate it, and integration will be, oh, sorry, this was e to I omega k1 to t. So the only thing that's dependent on time will be this exponent, and we integrate it.
So can you do a kind of normal form analysis of this, or what? Are you already?
Well, okay, so normal form analysis is actually would correspond to, okay, so okay, so we are in the box, right? And here's our k, and the Fourier modes are discrete, right? So what actually is important, and I'll probably not will have to skip a lot of detail, but this is important point. So that in wave turbulence, the limit L tends to infinity goes first, and then the limit of epsilon tends to 0, or t tends to infinity second after. So this means that all that frequency resonances you get, they actually will have to be considered broad, and they have to include many modes, because first you take this frequency broadening is because of nonlinearity, and these modes get more and more dense as you take a box to infinity. So in wave turbulence, it's a limit where you have a lot of modes inside. The normal modes would be the opposite, my understanding.
Okay.
Yeah. So, okay, so you get for B1, if I just substitute B0 here and integrate, so I Okay, so then okay, let me just be schematic, I guess. I want, what do I want after this weak nonlinearity expansion? I want weak nonlinearity expansion on z. Okay, so I want z at time t capital. And then I'll have to substitute my weak nonlinearity expansion in here. So I will have to, so e to lambda L, and substitute here b naught plus epsilon b1 plus epsilon squared b2, right? And then I Taylor expand that and in epsilon, this exponent, and I will get well, first term Taylor expansion will be just this squared, so it will be just z of 0 plus will be epsilon term plus will be epsilon squared terms, and epsilon squared terms will contain, as you might see from here, things like that will contain b 1 squared will be cross term bz, that will be some coefficients dependent on lambda. Okay, so that I will have to average. Okay, so and the averaging I will have to do first with respect to the phases. Okay, and things like that will not depend on phases. So, and to do phase averaging, I just use Wick's theorem, so they kind of see which terms pair with each other. And from this will die from, because it will contain only odd number of modes. So phase averaging. Yes, 0. So and this will give me the evolution equation, because I will group. This will give me something proportional to time times something, right? So I will divide the whole thing by time and say, well, z dot is approximately z of t minus z of 0 over time. Okay, and this something will be my evolution equation. And then I do the Laplace transform. So I'll write, okay, so and then what's important, okay, you see this is because t is less than the nonlinear time. I can do this approximation, right? Now, but t is greater than the linear time, and therefore when I average things like that, okay, so this will lead to me to delta function in omegas. So I'll just write an equation for you for well, I have to say, no matter what I do, I always fail to say anything sensible in 1 hour. So about that, I mean, it's a bit, no matter how simple you choose the system, so that's a bit frustrating. But let me write a sort of equation for you already for PDF. So it is like this. And so it's obviously it's continuity in probability space, beta b to conserve probability, total probability, normalization, and the flux, probability flux, is equal to so minus sk gamma k. So these are the pieces that will enter the kinetic equation. So these are some integrals. Well, let me just say schematically, the integrals of the kinetic equation. So essentially, if, well, for example, well, okay, so let me multiply by S, so get the equation for n. So n, the spectrum is the moment of PDF, right? So equation for n, the familiar kinetic equation, will be if I multiply that by that n, and so I'll get simply flux integrated from 0 to infinity. And if I do that, I actually get gamma k m k minus eta k. So, and this would be the kinetic equation. So now, one thing, perhaps, very important that I want to say, can do right here, right now. So is that, okay, so maybe you heard before Zakharov or somebody else talking about the Kolmogorov type solutions. We call them Kolmogorov-Zakharov solutions. So K, Z solutions, so they correspond to cascade of energy over K space. Now, one thing you can see here, that this solution to the probability equation, a steady solution, corresponding to flux equal to 0, and this is just P of the form minus S over N. Okay. So this is a Rayleigh distribution, which corresponds to Gaussian statistics. But there is a solution for f not equal to 0, and asymptotically for large S, it behaves like Paul law. So and of course, I mean, to normalize the solution, it better be cut off. So the picture is like this. So you have, say, a log of n of the probability and intensity. So you start Gaussian in the core of distribution of waves. Then it goes to that intermittent tail, and then you cut off somewhere here, which corresponds to wave breaking. Wave breaking means there is no waves with amplitude greater than something. Okay, so here's wave breaking. Okay, and so I guess the very last thing, maybe I'll say here, that actually you can try to combine, to relate how this Kolmogorov solution in the cascade in K space relates to flux in the amplitude space. And the picture I could draw is like this. So K, and here's the amplitude, and I force my waves here, and it forms a spectrum, which is KZ spectrum. So the mean value, okay. And then there is another curve here that corresponds where weak nonlinearity breaks, okay. And you can call it Phillips spectrum. Okay, so here nonlinear term is of order of linear. So what happens with the cascade, energy cascade? It actually goes to the point where the nonlinearity fails to be weak, okay. And so at that point, you form white caps, the coherent structures. Coherent structures contain all the harmonics. Okay, that's why they're coherent, right? So they will contain all the components with where nonlinearity balances with linear term, everything on this term. So part of them will go in dissipation due to white capping, for instance, right? So energy will get dissipated. And they will lose their coherence, and they will recirculate their energy back into the incoherent component, which will correspond to this flux like that. So this is flux in the amplitude space, So you have this kind of cycle going on. So partly recirculated energy back in the system. And you notice here, so this minus sign here. So the flux is actually from large amplitudes to low amplitudes. Okay, well, okay, that's not all I wanted to say, but you know, I think maybe it's enough.
I'm afraid not that much time is left for questions. Maybe one urgent question.
But this is an effect from the condensate that you were explaining at the end, or not?
That in condensate it would be for inverse cascade. It's other way around. So this is but
This is a short.
this is direct cascade for energy.
Reflecting back from the short distance cutoff.
Right. Yes, that's right. So, but with condensate, you know, this is some
That's another matter.
picture Alan New advocate. So inverse cascade will also lead to breaking of small
So
nonlinearity,
you have both
creation of collapses, and collapses will burn part of the energy and partly return it back to the system.
Okay, we have to move on, I'm afraid.